Okay, so to review, recall that we have silver atoms. The silver atoms have an unpaired electron, so they're either spin up or spin down. I mentioned to you that electrons in a closed shell do not have any magnetic properties. We can do things like go through an X-polarized Stern-Gerlach device, or to divide things in, and I'll use ket notation. We're going to catch the plus, the spin up ones, block the spin down ones. We can then go through another Stern-Gerlach machine. We're going to polarize this into Z. And then we can see that that is also spin up or spin down. We can block the negative ones. And we can play this game all day long. Now the weirdness is that, remember, you shouldn't see these things either go up or down. There should be a distribution, because if this is up, it'll bend upward. If the electron is pointed down, it'll bend down. But these things don't know gravity. The magnetic moment of that 5s electron can be in the plane. And it's not that like the quantum weirdness is that it's not, it is. And that's because the X works too, right? So, okay, so in my coordinate system, this is plus X and this is minus X. That's plus Z, that's minus Z. So, so it's not like the X and Y polarizations can't exist in 3 dimensions. That doesn't make sense even in quantum land. What doesn't make sense is how it just goes either up or down. And I have no explanation beyond that. This is just how it is, okay? We can do things like go through Z. Now, as I mentioned last time, you can go through X again, and you'll find that the polarization, so I call this polarization. When I've kept one and killed the other, that's polarized. If I go through another X, it's lost its polarization, 50-50 plus minus, just by having killed it off at the beginning. Okay, we talked about basis sets with kets, so that's a ket. It has a matrix representation. We'll fluidly go between, and this is how the book notates it. I will use matrices when convenient, because why wouldn't I? So you're going to see lots of switching back and forth between matrix representations and whatnot. Okay, and I'm consistently, when I'm writing these matrices, I am using an SZ basis set. Okay, now I'm going to trust that you remember Y, what Y is. It has a imaginary component. And here is SX plus in the SZ basis set. And so already, you know, it's not too bad, right? I mean, you can see that this is certainly getting a little complicated, but hopefully your head isn't blown off. It will be today. Today, I'm going to show you the true complexity, on and on and on. That's why. I'm going to show you the true complexity of Dirac notation today. So today it's on. Let's put it that way. The way to really understand this is we're just going to have to do it over and over and over again, because there's just really no other way to understand this. So that's going to be my approach. So remember that this is a ket. So now be very generic. That's a ket. A ket, remember, is a state. What that means, that's a very nebulous definition. You know, what does it mean? A state of mind, a state of being, all of those things. It represents the whole universe, right? So this is the ket of the universe and everything in it, including the cats. All right, that's fair. What do you do with it? Okay. So other than getting a little bit of a taste of X and Y and why we need quantum mechanics, let's talk more about kets. We which is not gonna, again, it's not gonna start out too difficult. You can add them together. Now, the analogy here is e to the ix plus e to the minus ix, right, equals 2 cosine. So, okay, not mind-blowing, so they add, really want to think of them like vectors. Now remember the term eigenvector, eigenstate, wave function, those are all the same thing. Eigenvector, you kind of, that's this property, that's the vector-like notation property. Okay, they can be scaled. And that's kind of like, plus minus. So you don't turn a plus by multiplying it by minus, by the way, and that's because the SC plus is different than SC minus. Oh, well, here's an example of throwing in a negative sign. So the SX minus, you throw a minus sign at the SZ plus component. There you go. So minus sign. So you can have minus signs. Now remember, one reason they look like this is because they are orthonormal. Remember that orthonormal, and this is an undergrad level idea, so I'm kind of counting on you to know that. The complex conjugate of state, I'll use my notation. I'll use my notation there. Okay, if these are the same wave function, e to the ix times its complex conjugate, e to the minus ix, then the result is 1. If these are different, then the result will be 0. Now, the way I wrote all of these, this is enforced. You don't, now remember I told you, hopefully you're looking at that saying, oh, okay, but I haven't shown you that. I'm telling you it's true, but I haven't shown you it's true, which is what we're doing today. Okay, anyway, so I forgot what I was talking about. Talking about this, all right. Now here's where the you know what hits the fan. Okay, now we have the bra. You've probably heard Dirac notation is called ket-bra notation, bra-ket notation. Okay, so what's going on is, this you've seen, and now you're going to have to deal with this. It's a ket drawn backward. I mean, it has to look nice and open and blow up. There we go. Okay, so I just drew a ket backward. Now you've seen a little bit of this already. Let me also point out that alpha plus beta. And this symbol even means something, and again, I'm getting into that. Okay, so there's a thing called a bra. I will explain what it does slowly and painfully over the course of several lectures. It's like a ket. Actually, it's not really like a ket. I don't know what the hell it is. I know what it is because I spent so much time on it. So let me give you its properties, then we're going to start doing things with it. And as we do things with it, it will become more apparent to you what it does. And I just can't really explain it. Okay, so this is called, this property here, this is called dual correspondence. That's the property, dual correspondence. For every ket, there's a bra. Now, you can either remember the word dual correspondence, or you can remember for every ket, there's a bra. You can also remember that's the same thing. This is a term you will see frequently in seminars. That's what it means. It sounds like a complex concept. It isn't. It's just what it's called. Okay, now here's a wacky thing. This one's kind of important. Okay, if you have a scaled state, its raw form, the scaled number goes to a complex conjugate. Now remember, all right, complex conjugate means that the imaginary component picks up a minus. If it's already negative, it becomes positive. It may not, if this is the square root of 2, see, I love doing this to undergrads. So I tell them this is like how I get them to think. The complex component is negative. And then I give them a real number. And I say, what do you do? And they, well, that's negative. I'm like, well, that is the real component? So why did you make the real component negative? And they look at me, I'm like, so what do you do when there's no imaginary, right? So it's 1/2, it goes to 1/2. It's only the imaginary component. It's just funny to me how they really struggle with that. And of course, if you have both, and I'm going to need to make sure that there's no reason to think these are the same coefficient. In fact, it would be very unlikely. Same deal. So, sometimes you probably can kind of guess that it would work this way. But see, and that's my biggest problem is getting it straight. Okay. Oh, and that was awful. There, here we go. Plus. Okay, that's a much nicer looking plus. Okay, so again, you can probably intuit that. Okay, now what? All right, so a bara's purpose is to project onto a cat. Now there's a whole bunch of words. What does that mean? This is a projection. I'm going to project beta. It's like I'm multiplying it, but not really. You'll see. Okay, this is a projection. I've even shown you this symbology before. Okay, if you don't remember, that's why we're having this class. Okay, so this was that.
You go full step. So bra for C alpha complex.
Oh, right here. See, I did it again. That's what you meant, right?
Yes.
Yeah, thanks for pointing that out. Yeah, so please catch me. I'm really bad about reversing the Broadway cat. I don't mean to. Just kind of easy mistake, right? Okay. Okay, so this operation here is the power of Dirac notation. This is the part that saves you 90% of all mathematics at the expense of having to learn how to do these operations, which unfortunately, well, they're complex. But way less complex than not doing it at all. That's the point. Okay. Bra and a cat slam together and form an inner product. And this is a number. It is a number. It is probably a complex number, but a number nonetheless. I don't even want to say it's a complex number because at this point, you should just assume that everything, look, everything's a complex number. Real numbers are complex numbers with 0 imaginary component. So I'm not even going to say that it's a complex number. Okay, more properties. Let me wipe this out. And this is all in your book. And I'm just writing it again because you just need to see this over and over again. There really is no, it's like, math class where you really just got to do it over and over again. Seeing someone write it up who knows what they're doing just doesn't do it. If you start writing this down, you're going to completely flub it up. You saw me make some mistakes there. That mistake was actually kind of bad, by the way. Given the rules you're going to see, the mistake I made, that was a pretty serious mistake. Okay, anyway, so we just talked about how 1 over the square root of 2 e to the ikx, 1 over the square root of 2 e to the minus ikx. So you're seeing some behavior that's hopefully kind of familiar. Now it's in ket form. Okay, so then if I do the projection the projection in the form of an inner product, and I'll explain projection. And notice that I'm doing like the associative axiom of mathematics, of algebra. So again, hopefully you're not blown away yet. It's just interpreting what this means. Now let me give you another one. Let's say beta. Now this is, I'm just writing this just for alpha. Beta is just beta. Now what I'm going to do is I'm going to say beta is in the form of this form, a sum of states, sum composed of two kets. Right, what I'm doing different here is that now I'm going to make beta the bra. And again, hopefully you could intuit that it's this. And I'm not saying alpha is this. Alpha is just, I'm saying specifically it is not this. I'm not using this here. So I got confused when I was reading my notes. Like, why wasn't there more alphas? There's just one alpha. I'm just showing properties. So be careful. These are not flowing together. These are two different examples of how to deal. What are the properties of bras? How do they work? And again, it's really following kind of middle school algebra rules. You know, you can do things like FOIL and whatnot. Okay, so last bit. This one is actually going to be a little bit more painful when you do proofs than it appears. You're going to have to do a proof, and it involves this, and it actually will really make your eyes bleed. That's coming up in the two problem sets. Anyway, if you reverse the roles, bra to ket, reverse them. Remember, I already said this is a number, so if you flip them, then it becomes a complex conjugate. Okay, now this one is a little, I don't like this one too much, but actually I do use this in a proof, so if you need to know it. Okay, so remember, again, inner product, that is the term, inner product. It is a number, generally a complex number. 0 is a complex number, just to, excuse my language, shitty one, right? So an inner product of a state with itself is greater than 0. Now what you're seeing here actually is a little bit of the uncertainty principle. We're getting to that. I'm going to use this when we solve the uncertainty principle, but that's like a month away from now. I just want to point out that if you kind of remember the uncertainty principle, you may remember that it kind of looks like that. Now, what I don't like about this is this statement. If alpha is a null ket. Okay, now a null ket represents nothing. And so this is stupid because why am I creating a ket for nothing? That's where I look at this stuff and I have a problem with it. What am I even talking about? So a null ket means that you're describing nothing. It turns out, again, in a month, I'm going to need this to prove the Heisenberg uncertainty principle. We're actually going to prove it. I think you were given, it was given to you as undergrad, we're going to prove it. And I need this, although it's stupid. Okay, now last one. And you're probably going to get a little bit, now I'm just going to show you a little bit more about what this stuff is. This is the norm. Sound familiar? Sounds like a normalizer, right? That is the norm. And let me go over here. So the other room that they could have given us is smaller than this one, but it did have a larger, it had a 2-panel whiteboard, but then it was half as wide. So I thought we were going to lose no matter what. Okay, so what does this mean? And let's do the norm. Okay. That means a normalized state as represented by a ket is this. Now, you may recall that as we were doing sine kx and e to the I, ky, and all that jazz, normalization was 1 over the square root of the integral of the complex conjugate times the wave function. Right? So, again, hopefully this isn't like super uncomfortable because you've already seen stuff like this. Okay, so we've talked about this before. And now you're kind of saying that, well, I think that is actually this, and very good. And I even told you that before. So you're starting to hopefully see what this Brockhead stuff does. Okay, so now what I want to do, I feel like I'm on the wrong page. All right, so with this, what I'm going to now do is start talking about operators. And the point that, so I hate to like seem to be going off in a different direction to talk about operators, but operators are actually bras. So I'm actually going to still talk about, so I'm going to like switch subjects, but I'm not going to switch subjects. I'm going to appear to switch subjects, but I'm not. I'm still telling you what bras are. Kets are kind of easy. You kind of already figured out their wave functions. That's not fully true for a reason you'll see in a while. But this probably isn't that hard to understand. This thing is a nightmare. All right, trust me. And I'm going to start to introduce to you other than, now you kind of you get a little bit of a flavor for it here. Of course, it's going to get worse. So let me talk about operators and then incorporate bra, and to show you how operators are actually bras, and you're going to get it more and more and more. And of course, you're going to be really good at this once you've done this 1,000 times. And one reason I did this is because, one reason directed this is because, again, it does save you on the mathematics, but the rules of this Brockhead stuff, this is how quantum mechanics works. So as much as we're going to do a lot of symbology here with a bunch of its own rules, you're actually learning the rules of quantum mechanics at a very deep fundamental level. And it may not seem like that, but that is what's happening. Okay, so now let's go back to operators. Now remember that. Remember that's my generic operator. I usually used it for, up till now, that's like momentum. But it could be position, it can be angular momentum. It can be a ladder operator. A ladder operator is something that will take a ground state and turn it into an excited state. That's a crazy thing. You'll see one of those in about a month. So, operator. Okay, now a linear operator does this. And I believe, I think all our operators are linear operators. I hope. And hopefully you can look at this, and again, intuit that, what is intuit? It's like a guess that's probably correct, right? Okay, so you can intuit that this is what it, that would be astounding, there we go, all right? So that is a linear operator. Try not to fall asleep. Okay, now notice it acts on the right. Acts on the right of a state. Now notice that this is looking very similar to like our eigenvalue equation. If the operator happens to be Hamiltonian, which remember we call it special, then I write the wave function to the right of it. And then it does what it does and spits out energy. But it looks similar. Now let's go into bra land. X on the left of a bra. Okay, so that means that if I have this, And like here, if this is the Hamiltonian and this is some wave function, it gets energy, this will do something too. And we'll get there. If this is a Hamiltonian, and if that, and I'm again hinting a bit more, if that's the dual correspondence of a state particle and box, then it actually spits out the energy times that bra. So it's slightly more familiar to you than you think. Okay. Oh God, I hate this one. Okay, this is the worst. The good news is this is the worst. It'll get easier from here. Oh God, how do I do this? All right, now that I've shown you operators act on the right of kets, on the left of bras, now I got to show you this one. Okay, so let's, and I'm hopefully using the same notation as the book. Okay, now just like, oh, I freaking wiped it out. Just like bras can be kets, and if they have a number, then it becomes a complex conjugate, the little thing you saw a minute ago. Then this can be turned into this can be turned into this. Oh, you need to have. Okay. That is a cross. It is not a star. You want it to be a star because that's a complex conjugate. It is not a star. It is a cross. Okay, this is called the adjoint. The adjoint. What does that mean? To this day, I still don't know myself. I swear to God, I know how to work the thing, but I really don't know what it is, to be perfectly blunt. Now, I'll give you something that is very obvious. The one thing I know about adjoints is this. Here, let me. The one thing I know about adjoints that might be useful is, and hopefully, I know I put this in my silly textbook, and you should know this. You should know this by now, and if not, come by office hours. You should know about Hermitian operators. Right? Hermitian operators are all the operators you've seen so far. They have real eigenvalues, and the states of that operator are orthonormal. And I wrote orthonormal earlier. Okay, now, if an operator is equal to its adjoint, it's Hermitian. Now, the hermiticity of operators, it's a mathematical property. All right, this is one way to put it. We will, I don't know if I'm not going to get to it today at this point. Thanks for forgetting the damn thing. I will do a proof of what it means to be Hermitian. I will give this a very specific mathematical identity. The result is a definition. It's a now, this definition, what does this mean? This is garbage. At this point, this is garbage. This is a star. That's not a star. That's a cross. That's a cross, and there's no cross. What the hell does that mean mathematically? It means nothing. I will show you in real math terms, what this means next time. The result of the formal definition, because this isn't it. This is nothing. This is a bunch of ink. The real mathematical definition of a Hermitian operator means the eigenvalues are real. It means that the wave functions of said Hermitian operator are orthonormal. Okay, that's coming up. So I don't want you to look at this and say, well, I don't know what that means, because I don't write it. It's just a bunch of ink at this point. Okay, let's see. Other properties. So again, I've written a bunch of stuff down. Now, if you're thinking like I'm not really getting it, you should. I haven't really shown you anything yet. I'm just giving you a bunch of symbologies. The symbols will have meaning next time. I just want you to get familiar with how they look. And again, I just don't have time to tell you what they actually do. Because again, these symbols, I get them, but I've already done all the example problems, so I know what it means for them. So this is the associative. This is the associative one, and this will be kind of important in one of your homeworks coming up. Okay, so that's associative. Okay, now again, one of the times that these things can be earned, probably not commutative. Okay, this is actually rare. Now, of course, that means if xy generally is not equal to yx. Do not assume that. That is a very bad assumption to assume that this is true. No. It might be true, but that's going to be unusual. Again, when you see what these things are, you'll get it. Especially after you've worked 50 problems on it. Okay. Let's see, bullet points. 2 operators equal a third operator. So what that means is that I can say x and y, 2 operators right next to each other. I can equate them to just to say it's 1 operator. Now, okay, here's an example. And again, I'm foreshadowing. You've already seen operators, by the way. You've seen momentum. Derivative, derivative. Okay, 2 derivatives in front of each other is what kind of derivative? Double derivative. Okay, momentum. Momentum squared over 2m is kinetic energy. Okay, so, all right, you get it. So I could have told you kinetic energy, or I could have said momentum. And I'm saying the same thing, over 2m. Mass, it's a number. So there you go. Okay, then there's this. Okay, this is silly. Okay, now you're starting to, now I'm going to show you a little bit more about what an operator is. Okay, so I showed you an inner product. And I'm not going to write that down because I don't want you to get confused, but you just saw it. So I said bra ket, but now I'm doing ket bra. I told you this stuff. I mean, it's just a couple little symbols. How many ways have I already like done stuff? Okay. That is this. I can go ahead and tell you this is an operator. It's called a projection operator. So this is a form of operator. So now you're getting a little bit of a better idea of what bras do. Bra ket is an inner product. It's a number. Ket bra is an operator. And that particular operator is called a projection operator. You haven't seen one of those yet. Okay. Okay, and by projection operator, so what that means is we turn a ket into another. Okay. So this would be like e to the ikx, forward wave. A projection operator would turn the forward wave to a backward wave. That would be like what a projection operator. E to the ikx, do its operation, do the projection operator thing, and now it's e to the minus ikx, a backward wave. That's the kind of thing projection operators do. They're very, very useful. And if you did this without raw notation, it's hideous. Mathematically, it's like mind-blowing. You do this with broadcat notation, it's just this. Where am I at? Okay, so let's do our projection operator. There's our operator, and it is going to operate on a state, let's call it gamma. Oh, that looks like a weird 2. Gamma. Okay, and what you have is now, sorry. Okay. Now you could also write this, so you can see the symbology actually makes sense. Let me write this in a way that looks a little bit better. Okay. All right, so what's happening is, this is a gamma ket. It could be a dog. What the action of the operator creates an inner product. Now that's a number, it's 5. Alpha is a cat. Okay, so this dog and this operator turned into 5 cats. That's what it did. Notice that since this is a number, I put it here because it is pleasing to the eye, but as a number, it technically can go out front. I don't have to complex conjugate it. That part is actually relatively easy to understand. Okay, so I got enough time to just show 1 or 2 more properties. Let me get the door. I wish I could end early, given that I screwed up with the camera. Let me just show a couple more properties, just a minute or 2. And you can forget about this until after the exam. Okay, now this is going to seem silly, but it's hideously important. Okay. Let's have an operator go inside of a inner product. So beta alpha, we're an inner product, it was the number 5. But what I'm going to do is I'm going to put an operator inside of it. And again, we'll figure out what this means. With, examples that can be like done on Mathematica. Okay, now this is nutty. I know this is like, it looks meaningless right now. Okay, what I'm saying here is that you can either let the operator do its work on alpha or have it do its work on beta. The residual, then, that's another question. What happens after the operation? Let's not worry about it. There's more stuff, but we're not going to worry about it yet. Okay, one more property. These are important, so I'm putting this why I'm putting bullet points here. This stuff's important. Okay, what I'm going to do here is I am going to, you're going to need this in a proof. It's a really hard proof. And so it's coming up. Oh my God, look at this. It's not that bad. What I've done is, you've seen this before. The operator's on the ket. So I flipped it over, so now the operator's on the bra. Now remember, that means you get an adjoint. Now the operators you've seen, that actually means nothing. The operator's equal to its adjoint, so that doesn't actually mean anything. Okay, but if I'm going to turn this ket to a bra, then that bra's got to become a ket, or you're talking mathematical junk. That's like, if you don't turn this bra to a ket, then you're using like the eigenvalue equation, but the wave function didn't come back. It certainly is a mathematical operation, it's just meaningless. So if you're gonna turn that ket to a bra, that bra better become a ket. Now, when you're switching bras and ket, and I showed you that earlier, you got a complex conjugate. So you got two things going on. If you're gonna flip this sucker over, you're gonna have to make an adjoint and you're gonna have to make it a complex conjugate. Adjoint because the operator is now acting on a bra, and because you flipped bra and ket, you also have a complex conjugate. Don't forget this one. I'll point it out when you need it again. Okay, and then the nice symbology, the way that this is actually written is like this. Okay, I'm just trying to make it more clear there. The last one, and this one is important. If your operator is Hermitian, like all the operators you've seen, then you do have this, which is nice. Now, I just used the fact that, so I simply didn't, this is kind of maybe a little silly, it's easy. There really is no adjoint. It's not that they don't exist, they're not zero. It's just you don't need to think about them if you have a Hermitian operator. So there's no need to put a little star not a star across. But notice I still flip bra and ket. I still flip those, so it still gets a complex conjugate. So, okay, next time I will start using these things in a in a deeper level so that they're not just a bunch of crazy symbols right now, so that all of this actually starts making sense. The only thing you should have gotten out of this is a whole bunch of wacky symbols that do wacky things. That's all you should have gotten out of this. But next time, we're really going to get into some more detail, and then this should start to get more meaning.